Hey everybody, this video is to take a look at the 4.2 day 2 notes. And in this video, we're going to look at concavity and what's called the second derivative test. So we have a graph here we're going to take a look at. And what we want to do is says consider the following function. Where is the graph concave up, meaning opening upwards? Where is it concave down, opening downwards? And we also want to go ahead and draw a sketch of a few tangent segments at each interval. And then sketch what the estimate of f prime looks like. And from there, we can then go ahead and sketch what f double prime might look like. So first off, when we talk about concavity, we'll look at when is it concave up first. So the graph is going to be concave up, as it said, when the function opens up. Guys, that in this particular case is going to start approximately here, and you're going to be concave up, until just about right there. We might be a little bit closer to there in terms of when it changes from concave up to concave down. So we can say that the graph is concave up from approximately 1 to 2.5. And then the graph is going to be concave down when it's opening downwards. So that's going to start at 0 until we hit 1. And then it's going to be concave down again from 2.5 till approximately 3.5 based on what we can see on the graph. Now, we don't know what necessarily is going to happen after 3.5. The function may continue to stay concave down. It really just depends on, the function. But for the interval that we can see from 0 to approximately 3.5, those would be your intervals when it's concave up and concave down. The next part of this was asking us to go ahead and sketch some tangent lines to graph the derivative. Now, some things that some points that are easy to identify are when you have those horizontal tangents. So we're going to have a horizontal tangent line right here. And what that tells us is the derivative is 0 at that point. So we can go ahead and come down here and plot a point with the derivative being 0. Now, the other horizontal tangent, it's not quite at 2. It's probably a little bit more here. So we could put the point there. And then we have another one, it's pretty close to 3, probably not right at 3. It might be a little bit more right there. Now, from there, what we know is we know the tangent's going to be positive here, and it's going to be, negative in all of these values. So one thing that tells us is that the derivative, while we don't know exactly what it's going to look like, it's going to be positive before that 0, and then it's going to be negative, and then come back eventually. Let's try to be a little bit. And then it's going to come back eventually here. And then the slope becomes positive again, so it's going to come up and then come back here, and then the slope becomes negative. So the derivative is going to have some kind of shape where it looks like that. All right, when the function is increasing, the derivative is positive. When it's decreasing, the derivative is negative. And then from there, it wants us to do the same thing for the second derivative. So we'll go ahead and label the red graph as f prime. And then here, if you did the same thing, you've got a horizontal tangent line of the derivative there. That means the second derivative is going to be 0 right there. You've got a horizontal tangent line. In this case, it's going to be approximately here. So which means the second derivative is going to be 0 there. And those would be the only places where you have those horizontal tangents. Now, the tangent line over here for that derivative is going to be negative. So the second derivative will be negative prior, and then it's positive. So you're going to get some type of a shape where it looks like that. And those aren't perfect graphs, but it gives you an idea of the relationship between a function, its derivative, and its second derivative. Now, the key thing that you want to kind of try to recognize here is that the second derivative is 0 here and here. All right? Our particular graph changed concavity here, which corresponds to that, and here, which also corresponds to those points. So there's going to be a relationship between concavity and when that second derivative is equal to 0. And that's one of the things we're going to be taking a look at here as we get going. So in the notes, you guys are definitely going to want to read through these and make sure you understand what they're saying. I'm going to go through them quickly. The definition of concavity says that let f be a differentiable function on an open interval from a to b. If the first derivative, so f prime of x, is increasing over an interval, then f is concave upward for that interval. So if the derivative is increasing, the function is concave up. If the derivative f prime of f is decreasing over an interval, then f is concave down. So if the first derivative is decreasing, the function's concave down. If the derivative f prime of f is not increasing or decreasing for the value of c, then f of c might be a point of inflection. Now, a point of inflection is where the graph changes concavity from either concave up to concave down or vice versa. So if we're looking at it from that standpoint, we need to know, is the derivative increasing or decreasing? And that's not always the easiest thing to determine. Another way to rephrase that is to think about it in terms of the second derivative. All right, so if we rephrase that, we can say let f be a differentiable function on the open interval from a to b. If the second derivative of f is greater than 0 on an interval, then f is concave upward. Now, you might remember from earlier in the units, if a derivative is positive, the function is increasing. So when we tie that to the second derivative and the first derivative, if our second derivative is positive, that means that the first derivative is increasing. So we want to think about concavity really in terms of the second derivative. When the second derivative of a function is positive, that function will be concave up. All right, so it's going to have that particular shape. And you could have put the same thing here. If the second derivative of a function is less than 0, meaning negative on an interval, then f is concave down for that interval. So concave down, concave down. And then if the derivative of f equals 0 or undefined, all right, then f of c might be a point of inflection if f double prime changes signs at c. Okay, and this, guys, I apologize, this should have said if f double prime equals 0 or undefined. It may be a point of inflection if there's a sign change. And that really becomes important when we're talking about points of inflection, because with critical values, if a derivative is 0 or undefined, it's a critical value. The sign change determines whether it's a min or a max and which one it is. With points of inflection, all right, you don't have a point of inflection unless the second derivative is equal to 0 or undefined and that second derivative changes signs at that value. So that's kind of an important distinction between, talking about what are critical values versus what are points of inflection. Critical values are any zeros of the derivative or where the derivative is undefined. But for it to be a point of inflection, you have to have the second derivative equaling 0 or undefined and changing signs. All right, so that's kind of a key detail to make sure you pay attention to. All right, guys, that's a good introduction to 4.2 day 2. I'm going to go ahead and stop this video here, and we will continue part 2 of the video, or the rest of the examples in part 2.